Graph algorithms. Graph problem and algorithms. Often real-life problem can be scheduled as graph problems. Graph problems are an essential part of computer science as well as real-life scenarios. Thousands of interesting problems can be represented as graphs. For example, basic graph algorithm including traversals, connected component, etc. Representation of graphs. There are two standard ways of representing graphs. First is the adjacency list. A list containing each node which in turn contain the list of outgoing edges from it. Next is the adjacency matrix. This is a n cross n matrix containing number of edges between respective nodes. Both representation can be used for directed as well as undirected graphs. So this is an example of adjacency list. So if this is the graph and this is the list, for every node there will be a list for all the vertices it is connected to. For example, this blue vertex, this sky blue vertex is connected to yellow and pink. So you can see in this node there will be yellow and pink. The order is not important. Let us consider this. In this green is connected to this 4: yellow, deep blue, pink and red. So as you can see, 4 are present. So this is represented by numbers also, but the same concept. Next is adjacency matrix. Adjacency matrix is a 2D array of size v cross v, where v is the number of vertices. And let the 2D array be called adjacency adj. It is a 2D matrix. And slot every adj ij is equal to 1 if there is a edge from vertex I to vertex j. So there are 4 vertices, 5 vertices here. So 0 to 4 on both the sides we have rows and columns equal to 0 to 4, that is 5 rows and 5 columns. So 0 to 0 is not connected. There is a edge between 0 and 1. So we have a 1 here because of this. Also 0 is connected to 4. So we have a 1 here. Consider this 3. 3 is connected to 4, 1 and 2. So 3 is connected to 1. Here is 2 and here is 4. So this is adjacency matrix. Graph traversal algorithms. Graph traversing. Task of processing or visiting every node in a graph. There are two graph traversal algorithms, that is breadth first search and depth first search. These two algorithms differ in the way they discover the next set of candidate vertices. First we will go through BFS. Breadth first search initiates at a given vertex u which is at level 0. In the first stage we visit all the vertices that are at the distance of one edge away. When we visit there, we mark as visited the vertices adjacent to the start vertex u. These vertices are placed into level 1. In the second stage, we visit all the new vertices we can reach at the distance of two edges away from the source vertex u. These new vertices, which are adjacent to level 1 vertices and not previously assigned to a level, are given a level 2 and so on. The BFS traversal terminates when every vertex in the graph is visited. Breadth first search is so named because it expands the frontier between the discovered and the undiscovered vertices uniformly across the breadth of the frontier. So this is the example of breadth first search algorithm. So we will start with the first node. So this node is connected to these 3 vertices, that is these 3 vertices are one edge away from it. So we will first travel to this vertex, then we will travel to this vertex, and then we will travel to this vertex. So you can see that for this vertex all the 3 vertices that were one edge away from it is traversed. So this is now done. So it is turned into black. Next let us consider this vertex. As you can see, all the edges are coming into this vertex. From this vertex we cannot move anywhere. So this is also processed. Now let us consider this vertex. From this vertex we can move to this vertex we can move, then we are moving to this vertex. In this way, from here also we cannot move anywhere else. So these are all directed graphs. the figure is small, so the arrows are not visible, but this from this it is directed to here and here. So when these two are visited, this is also processed. So in this way, for each and every vertex, we travel all the vertices that are one edge away from it, and when the vertices are done, when all for a vertex, when all the adjacent vertices are covered, it is turned black. So in this way we process the similar procedure for all the vertices, and finally we will get a graph in which all the vertices are processed. In this way we will find the breadth first search, and the order in which the vertices will be traversed will be the breadth first search sequence. So this is the pseudocode for the breadth first search. Next, analysis. The runtime. We enqueue a vertex in O of one time. Adding the vertex to queue, it doesn't take much time. Hence, totally we have O of V operation or element present in the queue. Also, the algorithm scans the adjacency vertex of each vertex only after it is dequeued from the queue. Hence, it scanned only once, thus taking at most O of E time. So, also the overhead for the initialization step is O of V. Thus, the algorithm takes a total of O of V plus E time. So, for all of you who are wondering what is the queue, so queue is used in the BFS algorithm. That is, when we select a vertex, suppose we select this vertex, we will add this to the, this is the queue, we will add this to the queue, and then all the vertices that are traveled after that will be consecutively added. Suppose this is traveled after this, so it will be added. Next this will be added to the queue. Next this will be added to the queue. In this way, when for a vertex will turn black, that is for a vertex every adjacent node is visited, it will be dequeued. So in this way the queue is followed to maintain the BFS algorithm. Important properties of BFS. Let G is equal to VE be a directed or undirected graph, and let S be any vertex that belongs to set V. Then for any edge UV and a vertex S, distance S to V is less than equal to distance S to U plus 1. Let G be a directed or undirected graph, and the source vertex S, the distance V computed is greater than the distance S to V. Next is the depth first search. DFS explores the edges out of the most recently discovered vertex from which V has been discovered. Once all the edges leading out of V has been processed, the search backtracks to the vertex from which V was discovered. This process completes until all the vertices has been discovered. As in breadth first search algorithm, when DFS discovers a vertex V during the scan of an adjacency list of an already discovered vertex Y, it then stores V's parent as U. The parent graph of a DFS search tree is actually a forest, as it comprises of several depth first tree from multiple sources and the edges are tree edge. So this is the example of DFS algorithm. Let us say we start with A. From A we will try to move as far as possible. So from A we can move either to B or C. Let us move to B. From B we can move to either D or E. Let us move to D. So from A we are moving to B, from B we are moving to D. Now you can see that we have no other place to go because there are no other edges that is connected to D. So we backtrack. We backtrack to B and see if there is any other way to go from B. So there is E. So we travel to E. Again we will backtrack. B has no other way to go. So we will backtrack to A. Now A has one more way to go, that is C. After C we can travel either to F or G. Let us travel to F. From F there will be no other way to go. We will backtrack to C. C has one more way to go, that is G. From G we have no other way to go. We will backtrack to C. C has also finished its processing. Then we will backtrack to A. A has also finished its processing. So in this way DFS is done until all the nodes are discovered. So this is the algorithm, or rather the pseudocode for DFS, and it is similar to the way I have explained in the figure. So from the algorithm it is clear that the total cost of DFS is O of E plus V. The properties of DFS. Parent property. The parent or graph of DFS tree is indeed a forest of tree. Additionally, vertex V is a descendant of the vertex U in DFS forest if and only if V is discovered before the time U was grey, meaning U has been discovered first and then V can be discovered. If you are calling U as a parent of V, then first you have to discover U and after that you are discovering V. So that is the parent property. Application of DFS. Detecting cycle back edges are key to finding a cycle in the graph. If there are no back edge, no cycle exists in the graph. Articulation points. Articulation point are vertices which when removed disconnect the graph in the sense that there are some pair of vertices UV which are no longer connected and have any path in between them. DFS traversals help in detecting articulation point. Topological sorting. Topological sort is the most important operation on directed acyclic graphs. It orders the vertices on a line, that is, all directed edges grow from left to right. Such an ordering cannot exist if the graph contains a directed cycle. This is because there is no way in which we can keep going right on a line and still return back to where we started from. So the upcoming topics are single source shortest path algorithm and flow problems. Thank you.